Welcome back. Problem 7-46. So statement is the beam is subjected to shear of 800 Newton. Determine the average shear stress developed in the nail alongside A and B. If nail are spaced 100 millimeter apart, each nail has a diameter of 2 millimeter. So you can see this is the beam, and that is made up of these wood that are nailed together at side A as well as at side B. These nails are spaced of 100 millimeter and having diameter of 2 millimeter, and a shear of 800 Newton is applied. So you have to find the average shear stress developed in this nail. So let's start with the solution. We know that shear flow is equal to horizontal shear force per unit length, which is the space, and that shear flow is also equal to V into Q divided by I. So what we do is that we have this V, we do not have Q, we do not have I. So we'll find first I, which is section property. So for section property I, which is not known, so we will first find the neutral axis passes through centroid. So because this beam is not symmetrical about a horizontal axis, so we will first find the centroidal axis passing centroidal axis. So for that we have formula, which is y bar is equal to sum of y dash into a divided by sum of area. So let this is 1 and this is 2. Since A board and B are same, so we will write it y1 dash into A1 plus 2 times y2 dash into A2 divided by A1 plus 2 times A2. Now what is y1 dash? So if we take this upper surface as a reference line, so this is 1, so this area will be A1. So y dash will be equal to A1 is, you can see, 250 millimeter multiplied by 30 millimeter. Clear? So 250 millimeter in term of meter is 0.250 multiplied by its thickness, which is 30 millimeter, and 30 millimeter is 0.03. What is y dash? So y1 dash, so y1 dash is distance from the top surface till the mid of this first. This distance is y1 dash, and this y1 dash is 30 divided by 2, which is equal to 15 millimeter. So 15 millimeter is 0.015 plus 2 times A2. Now A2 is this area, which is 30 multiplied by 150 millimeter. So 115 is 0.150 multiplied by 30 is 0.03 into y2 dash. So y2 dash is distance from top surface till the mid of this second. This distance is y2 dash, and this y2 dash is 150 divided by 2, which is equal to 150 divided by 2, which is equal to 75 millimeter, and 75 is 0.075 meter. Divide by area A1. A1 area was 0.250 multiplied by 0.03 plus 2 times area 2, which is 0.150 multiplied by 0.03. So when you calculate it, you will get y dash, the location of neutral axis passing through centroid, is equal to 0.04773 meter, or you can say it is 47.73 meter. What does it mean? It means that from the top, the neutral axis or centroidal axis passing through its neutral axis, centroidal axis will be this one. So this distance from the top, this is your y dash, y bar, which is equal to 47.73 millimeter. Now you have I. So by using parallel axis theorem, we will find I, which is I is equal to sum of I dash plus AD square. So for first one, we will have 1 over 2, 1 over 12. I am talking about this one. So we'll first find the moment of inertia of this, which is equal to 1 over 12, its breadth, into h cube. H is 30 millimeter. So I will write 1 over 2, 0.250 in meter, into h is 0.03 whole cube, plus area. Area is again this 0.250 into 0.03 into d square. Now what is d square? So distance from neutral axis till the mid of this section. So this is your d1. This is your d1. So d1, you can see that it can be obtained if you subtract y1 dash from this. Clear? So y dash in meter is 0.04773 minus y1 dash is 0.015 whole square, plus 2 times 1 over 12. Now we will calculate the moment of inertia for this. So its breadth is 30 millimeter and height is 150 millimeter. So 1 over 12, breadth is 0.03 into height is 0.150 whole cube, plus area, which is equal to 0.03 into 0.150 into d square. Now what is d square? So d square is distance from neutral axis till the mid of second section. So this is the mid of second section, and this is the neutral axis. So this distance is d2. So I will write this distance is d2, and this can be obtained if you subtract y dash from this y2. You can see that if you subtract this distance from this distance, clear? So you will left with this. So this distance y2 dash is again that was y2 dash was 0.075 minus y dash, which is 0.04773 whole square. So when you calculate it, you will get the moment of inertia for the beam shown above is 32.164 into 10 to the power minus 6 meter power 4. Now you have this I, you have V, you do not have Q. So what we will find Q? We know that Q is equal to y dash bar into A. So you can see that here this is the shaded portion. This one is the shaded portion in which we use this nail to connect with this. So this is the area A dash. So this is A dash, and y bar is distance from neutral axis till the mid of this section, which is this D1, and D1 was this one. D1, this value, this one. So I will write it 0.04773 minus 0.015 into area. Area is 250 millimeter, which is 0.250 multiplied by 0.03. So when you calculate it, you will get Q is equal to 0.245 into 10 to the power minus 3 cubic meter. Now you have V as well, so you can just put it in this formula. Q is equal to shear flow, which is horizontal shear force per unit length, is equal to V into Q divided by I. So V is equal to 800 pound. Q is 0.245 into 10 to the power minus 3 divided by I, which is equal to 32.164 into 10 to the power minus 6. So from here you will get the value of shear flow is 6105.4 Newton per meter. Okay. This 800 is not in pound, this is in Newton. So can we make this correction? So now we have shear flow. We know that shear flow is also equal to horizontal shear force per unit length. So you can just put the value of Q 6105.4 is equal to FH divided by S. S is the spacing, nail spacing, which is 100 millimeter. So 100 millimeter in term of meter is 0.1. So from here you will get horizontal shear force will be equal to 0.1 multiplied by 6105.4, and we will get horizontal shear force will be equal to 610.54 Newton. Now this I will write it, since each side of the beam resists this shear force, then average shearing stress in the nail will be equal to FH divided by 2 into area. You can see that you have nail on this side as well as on these sides, clear? So the shear force will be divided by 2. So that's why FH divided by 2 into area. So FH is 610.54 divided by 2 multiplied by diameter of nail is given. So area is pi by 4 into 2 millimeter. In meter it is 0.002 whole square. So when you calculate, you will get the average shearing stress in the nail comes out to be 97.2 megapascal, which is the answer of this question. And that was all about this problem 7-46. I hope you have enjoyed this video. Those who are new to my channel, then I will request them to subscribe it, and don't forget to press the bell icon. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. Problem 6-88. This problem is taken from chapter number 6, that is bending, and book name is Mechanics of Material by RC Hibbeler. So statement is, if the beam has a square cross section of 9 inch on each side, determine the absolute maximum bending stress in the beam. So you can see this is a cantilever beam, that is, and A is fixed, and from A till a length of 8 feet we have uniformly distributed load, and at point B we have a concentrated load of 1200 pounds. And the cross section is that this is a square cross section 9 inch by 9 inch. So you have to determine the absolute maximum bending stress in the beam. So let's start with the solution. So first step is that if you remove this fixed support at point A, so you will be having a reaction force which is represented RA, and you will be having a moment which will be MA. So we'll find this RA and MA by using equation of equilibrium. So first equation of equilibrium is that sum of all moment about point A is equal to 0, and taking the counterclockwise moment as positive. So you can see this is counterclockwise moment, so it will be positive. So I will write MA. The second moment will be due to this load, which is 1200, and now perpendicular distance is 16 feet, clear, and this is producing clockwise, so it will be negative. So I will write minus 1200 into 16. The third load is due to this uniformly distributed load, so we will convert this uniformly distributed load into a point load, and that will act at the middle of this 8 feet. So this distance will be 4 feet, and this remaining will be also 4 feet. Now this distributed load, when converted into point load, so it will be equal to 800 over the length, entire length over which it acts. So this will be equal to 6400 pounds. Now due to this load about point A, the perpendicular distance is 4 feet, and it is also producing clockwise, so it will be negative. So I will write minus 6400 multiplied by 4 is equal to 0. So from here you will get MA will be equal to this 1200 into 16 will give you 19,200 plus this 6400 into 4 will give you 25,600. So when you add them, you will get moment about A comes out to be 44800 pounds into feet. So this will be the moment, clear? Now we will find this RA by using equation of equilibrium. The second one, which is sum of all forces along y direction, must be equal to 0, and upward force is taken as positive. So you can see RA is upward, minus this 6400 is downward, minus 1200 is downward, and their sum must be equal to 0. So I will write RA minus 6400 minus 1200 is equal to 0. So from here you will get this RA will be equal to 7,600 pounds. Now you have RA and RMA. So what we are going to do is that we will draw the shear force and bending moment diagram, and from there we will take the maximum bending moment. So what we will do is that we will take vertical line from the end of this beam, and similarly a vertical line from the other end of the beam, and then there is a horizontal line to show the length in feet. So X will be in feet. On y-axis you will take the shear force, that will be in pounds. Okay, let one division is 2000. So 2000, this is 4000, this is 6000, this will be 8,000. Okay, now at point A we have RA, which is equal to 7600. So what we will do is that we will plot 7600. Let 7600 is this point. Okay, now if you take a vertical line from this, so this length will be 8 feet, and this distance will be, the other one will be also 8 feet. Clear? Okay. Now we want to find the shear force at this point. So you can see the shear, this is the load which is 800 over the length which it act is 8, so it is 6400. So what we will do is that this is downward force, so this force will be minus 6400. So 7600 is there, minus 6400 will cause it to 1200, plus 1200. So over here we will have plus 1200. So let plus 1200 is this point. This is 1200. Now you can see that this load is straight line, clear, of 0 degrees, so shear force will be 1 degree higher, and it will be a straight linear line, and slope will be decreasing because this load is downward. Now moving from this point till end, there is no other shear force, so it will remain horizontal till end, and at the end you can see you have minus 1200. So plus 1200 minus 1200 will bring it to 0, so it will come down. So this is your shear force diagram. Now we'll draw the bending moment diagram. So for bending moment diagram, I will take a horizontal line to show X in feet, and on y-axis we have movement having unit pounds into feet. Okay, let one division, you can see the movement is in 10,000, so we will take one division is 10,000. So downward is minus 10,000, minus 20,000, minus 30,000. Similarly, this will be minus 50,000. Now at point A, you can see you have a moment of MA, which is 44,800 pound into feet. So this is counterclockwise. While drawing it on bending moment diagram, this counterclockwise movement will cause it to toward downward. So we will locate it as minus 44,800. So let this point is minus 44,800 pounds into feet. Now area under the shear force diagram will give you the bending moment. So this area, you can see this is trapezoid. This length is 7,600 and this height is 1,200. So how we'll find this area? Let this area is A1. So A1 will be equal to this height, which is 7,600 plus this height. So I will write it 7,600 plus 1,200 divide by 2 into this breadth, which is equal to this breadth, which is equal to 8 feet. This is how we find the area of trapezoid. Okay, so when you solve this, this area will be equal to 35,200. Now here the moment is minus 4,480 minus 4,4,800 plus this 3,5,200 will cause it to change it to minus 9,600. So at this length we will have minus 9,600. So let this point is minus 9,600 pounds into feet. Now you can see that this shear force is a 1 degree line and slope is decreasing. So bending moment will be the 2nd degree curve and it will be in clockwise direction. So you will join these 2 points by using this curve. Clear? Now the second area under the shear force diagram is this area. Let this area is A2. So you can see A2 is equal to this height. This is rectangle. So this height multiplied by this width. So 1200 multiplied by 8. So 1200 multiplied by 8 will be equal to 9600. So minus 9600 plus 9600 will be equal to 0. So bending moment will be 0 at this point. So our new point will be this one. Clear? Now you can see that shear force is a horizontal line with 0 degree and this is positive area. So bending moment will be 1 degree higher. It will be a linear line and slope will be increasing. So we will join these 2 points using straight line. So this is your bending moment diagram for this beam. Now from BMD bending moment diagram, we can see that maximum absolute value of bending moment is equal to, you can see one is this one, the other one is this one, and third one is 0. So this is the maximum value. So minus 44800, and unit will be pounds into feet. So this maximum bending moment absolute value will be equal to 44800 pounds into feet. Now if you want to convert it into kips, so 44.8, it will be kilopounds, which is equal to kips into feet. Okay. Now if you want to convert this feet into inch, so what we will do is that 44.8 multiplied by 12, and the unit will be equal to kips into inch, because 1 feet is equal to 12 inch. So this is the maximum bending moment. And we know that maximum bending absolute value of bending stress is equal to maximum bending moment into C divided by I. Since we have been given a square cross section of 9 by 9, this is 9 inch and this height is also 9 inch. So we will find the moment of inertia for this beam, and if we take the half of this will be its neutral axis, NA, and for this I is equal to, I for rectangular or square is 1/12 BHQ. So here B is 9 and H is also 9, so 9 power 3, that will give you I. And when you calculate this I will be equal to 546.75 inch power 4. What about C? So C is distant from neutral axis till top or bottom, so this are C, which is equal to 9 divided by 2. So C is equal to 9 divided by 2, which is equal to 4.5 inch. Clear? Now you have all the values. You can just put it in this formula. Maximum absolute value of bending stress is equal to moment, which is equal to 44.8 multiplied by 12. Unit is kips into inch divided by I, which is having 546.75 inch power 4, and C is 4.5 inch. So we will left with we will get 4.42 kips, which is kilopound, clear, divided by inch square, and that is maximum absolute value of bending stress. And when you calculate it, this is maximum absolute value of bending stress is 4.42, and kips per square inch will be equal to KSI, which is kilopound per square inch. And that is the answer of our this question, in which we have calculated the maximum absolute bending stress for the beam and loading shown. I hope you have enjoyed this video. If you are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. Problem 1-64. This problem is taken from chapter number 1, stress, and book name is Mechanics of Material by RC Hibbeler. So statement is a vertical force of P 1500 is applied to the bell crank. Determine the average normal stress developed in 10 mm diameter of rod CD and average shear stress developed in 6 mm diameter pin B that is subjected to double shear. So you can see this is the bell crank, which is applied a load of 1500 Newton, and this is the rod CD, which is used to support this bell crank. And there is a pin support at point B. So this pin having diameter of 6 mm, while this rod CD has diameter of 10 mm. So you have to find the average normal stress in this CD, and there is a pin. You have to find the shearing stress in that pin. So let's start with the solution. So if you take the bell crank free body diagram FBD, so what if we remove this pin support at point B? So you will be having a vertical reaction force, which is represented as By, and there will be a horizontal reaction force, which is represented as Bx. Always try to draw it separately for saving time. I'm drawing it over here. And the rod CD exert a force FCD in this direction. You can see that this force is downward, causing the rod, causing it to move outward. As a result, the rod exert force in this direction, which is FCD. So we'll find this FCD, Bx, and By by using equation of equilibrium. So first equation of equilibrium is that sum of all moments about point B is equal to 0, and taking the counterclockwise moment as positive. So about point B, first moment will be P into perpendicular distance is 450, and this is producing clockwise, so it will be negative. We will convert this 450 millimeter into meter, which is 0.45 meter. So P into 0.45. And I will also put the value of P, which is given as 1500. So 1500 into 0.45. And you can see that this FC is producing counterclockwise movement because perpendicular distance is this one and this is the force. About point B, it is producing counterclockwise movement, so it will be positive. So how we will get this vertical distance? So you can see if I draw perpendicular line, so this is 45, so this will be also 45, and this distance will be equal to, if you take sine of 45 degree, okay, let me explain it over here. You can see you have one, this FCD is 300 millimeters. So you can see you have one portion is this one, another one is this one. This is the perpendicular distance. So if you take sine of 45 degree, so it will be equal to, let this is y. It will be y divided by CB, which is 300 millimeter. So 300 millimeter. So y will be equal to, this is in millimeter. So y will be equal to 300 into sine of 45 degree. And the unit will be millimeter. So if you want to convert it into meter, it will be 0.30 sine of 45 degree. Now you can see this FCD and perpendicular distance is this one. Clear? This is a perpendicular distance and it is producing counterclockwise movement, so it will be positive. So I can write plus FCD into 0.30 sine of 45 degree, and it will convert, the unit will be in meter. Okay, now their sum must be equal to 0. So from here you will get FCD is equal to 1500 multiplied by 0.45 divided by 0.30 sine of 45 degree, and that will give you 3181.98 Newton. Now we'll find Bx and By by using another equation of equilibrium, that sum of all forces along x direction must be equal to 0 and force in this direction is taken as positive. Now you can see that we have one force Bx is in this direction, which is positive, and FCD is in opposite direction. Their sum must be equal to 0. So I can write Bx minus FCD is equal to 0. So Bx should be equal to FCD for equilibrium, and FCD is 3181.98 Newton. The last thing is that we can find the third force, which is vertical By, and it can be found by using this equation of equilibrium. So By minus this P, which is 1500, is equal to 0. So from here you will get By is equal to 1500 Newton. Now you have all three forces. So what we will go is that force in this rod is this one, FCD 3181. Clear? So what we are going to find, the average normal stress in rod CD, which is equal to force in rod CD divided by area of CD. So force in rod CD is 3181.98. Diameter of rod CD is given as 10 millimeter, which is equal to 0.01 millimeter. Clear? So we will use this, and diameter of it is equal to pi by 4 d square, and d is 0.01 square. So it is 3181.98, and diameter will comes out to be 78.54 into 10 to the power minus 6. Okay. Now if you further simply calculate it, so you will get average normal stress in rod CD comes out to be 40.5 into 10 to the power 6 Pascal, and you will get average normal stress in rod CD will be equal to 40.5 megapascal, which is the answer of our first part. Now we'll move towards second part, and in second part we have been asked to find the average shear stress in pin B. Okay, you can see here that this is By and this is By and this is Bx. So if you draw it by using head to tail rule, clear? So there will be a resultant force which will be B, and that will act on this pin B. Clear? So how we can find this? Because you can see one is vertical component By. Let me draw it. This is the B, this is By, and this is Bx. Clear? So by using Pythagoras theorem, B will be equal to Bx square plus By square under the root. So we will calculate this B by using Pythagoras theorem. So B is equal to Bx square plus By square under the root. Put the value, Bx is 3181.98 square plus By is 1500 square under the root. So you will get this B will be equal to 3517.81 Newton. Now you have this B. So you can see if I draw this pin like this, if I want to draw the pin like this at B, so this B is acting over here, and it is given that it is double shear because there are two supports, so VB and VB. So this shear force will be equal to, this B will be equal to 2V, double shear. So shear force will be equal to B by 2, and 3517.81 divided by 2 will give you the shear force VB on the pin, and this shear force comes out to be 1758.91 Newton. Now you have shear force. We know that average shearing stress is equal to shear force divided by shear area, which is area of this pin B. So put the value 1758.91. The diameter of this pin is given as 6 millimeter, which is equal to 0.006 meter. So what will be the diameter? So diameter is pi by 4 d square. D is 0.006 square. And when you calculate it, it will give you 62.2 into 10 to the power 6 Pascal. And in term of megapascal, it will be 62.2 megapascal. And that is the answer of our second part. And this was all about this problem 1-64. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. I will suggest you to try this problem by your own, and if you feel any difficulty, you can ask. Thank you. Welcome back. In this video, we are going to solve problem 1-83 that is taken from chapter number 1, Stress, and the book name is Mechanics of Material by RC Hibbeler. So statement is the 60 mm by 60 mm oak post is supported on the pine block if the allowable bearing stress for these materials are 43 megapascal for oak and allowable bearing stress for pine is 25 megapascal. Determine the greatest load P that can be supported. If a rigid bearing plate is used between these materials, determine its required area so that a maximum load P can be supported. What is that load? So you can see this is oak post and that is supported by pine block, clear, and there is a P load applied on it. So you have to allowable bearing stresses of both loads are given, so you have to find the largest load P that can be applied. And in B part, if there is a rigid bearing plate between these two, so you have to find the required area of this bearing plate for the maximum P load. So let's start with the solution. Now what we will do is that we will find this P for allowable bearing stress of this pine wood or pine block. We will find P. How we'll find P? So we know that stress is generally equal to force per unit area or load per unit area. So for this pine block, we are given this allowable stress for this pine is 25 megapascal. So 25 into 10 to the power 6 Pascal. So this pine allowable bearing stress will be equal to load divided by bearing area. Clear? So load is not available. And you can see that it is mentioned that this is 60 by 60 millimeters. So this is 60 and this width is also 60. So this will be the bearing area. Clear? So I will write this is 60 by 60. So I will in meter it will be 0.06 multiplied by 0.06. And allowable bearing stress is 25 megapascal. So 25 into 10 to the power 6 is equal to P divided by 0.06 multiplied by 0.06. So from here you will get this P will be equal to 25 into 10 to the power 6 multiplied by 0.06 into 0.06. So when you multiply this, you will get 90 into 10 to the power 3 Newton. And in kilonewton, it will be 90 kilonewton. So you will get this P. Now this P is calculated, that is based on allowable bearing stress of pine. Now what we will do is that we will find this P for allowable bearing stress of oak. And we will find P. So allowable bearing stress of oak is equal to load per unit bearing area. So load is not known and bearing area of this will be same as 0.06 multiplied by 0.06. And allowable bearing stress of oak is 43 megapascal. So I will write 43 into 10 to the power 6. It will be equal to P divided by 0.06 multiplied by 0.06. So from here this P will be equal to 43 into 10 to the power 6 multiplied by 0.06 multiplied by 0.06. And when you calculate it, it will be equal to 154.8 into 10 to the power 3 Newton, or in kilonewton, this P will be equal to 154.8 kilonewton. And you can round it off, so P will be equal to 155 kilonewton. Now you can see you have two loads. This is load based on pine, allowable bearing stress of pine, and this is the load based on allowable bearing stress of oak. And in question, we have been asked to determine the greatest load P. So our answer will be, answer of first part will be the greatest load P will be equal to 155 kilonewton. So this is answer of our first part. Now we'll move towards second part, and in second part it has been asked to find the bearing required area of bearing plate so that maximum load P can be applied. So if a bearing plate is incorporated in between these two wooden pieces, so what will be its bearing area? So what we will do is that you can take for this maximum load P, because it is given as maximum load P. So we know that stress is equal to load or force per unit area. So we will calculate this area of plate based on strength of pine. Why we are taking the strength of pine block? Because it is the smallest. There, so we will design on the smallest one, smallest strength. So you can see this is the smallest and this is largest. So we'll choose this value. So the stress is 25 clear into 10 to the power 6 Pascal. Sorry, it will be Pascal. 25 into 10 to the power 6 is equal to P is the largest load. So 155 into 10 to the power 3 divided by the area. So from here you will get this area will be equal to 6.19 into 10 to the power minus 3 and unit will be square meter. So this is the answer of our second part. And that was all about this problem 1-83. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching and supporting me. Welcome back. In this video, we are going to solve problem 1-85 that is taken from chapter number 1, Stress, and book name is Mechanics of Materials by RC Hibbeler. So statement is the beam is made from southern pine and is supported by base plates resisting on the breakwork. If the allowable bearing stress for the materials are for pine, it is 2.81 ksi and for break allowable bearing stress is 6.70 ksi. Determine the required length of the base plates at A and B to the nearest 1/4 inch in order to support the load shown. The plates are 3 inch wide. So you can see this is the beam clear that is made up of southern pipe, and there is uniformly distributed load from one end till the over the whole length, that is 200 pound per feet, and there is a 6 skip load at a length of 5 feet from this point A, and there is a base plate between this beam and this bricks clear. So you have to find the length of this base plate. So let's start with the solution. So first step is that if you remove this support at the brick, so there will be a reaction force. Let this reaction force is RA, and if you remove this bricks, so there will be a reaction force offered by this brick on this beam or base plate, which will be RB. Okay, now this 6 skip is equal to 6,000 pound. 6 skip is 6,000 pound, and when there is a uniformly distributed load of 200 feet, so when you convert this uniformly distributed load into a point load, so it will act at the half length of the beam, and this will be equal to 200 over the length which it acts. So total length is 13 feet. So 200 multiplied by 13 will give you 2,600 pounds feet, and it will act at the half. So total is 13. So it will be 6.5 from either sides. So this is 6.5 feet. Now you'll apply equation of equilibrium in order to find this RA and RB. So what will be the equation of equilibrium? So first equation of equilibrium, that sum of all moments about point A is equal to 0 and taking the counterclockwise moment as positive. So about this point A, the first moment will be due to this 6 skips or 6,000 pound load, and perpendicular distance is 5, and this is producing clockwise moment, so it will be negative. So I will write minus 6,000 into 5. The second moment is due to this load, and this is 2,600, and the perpendicular distance is 6.5, and this is producing clockwise, so it will be also negative. So I can write it minus 2,600 multiplied by 6.5. And the last load which is producing moment about point A will be RB into perpendicular distance is 10 feet, and this is producing counterclockwise moment, so it will be positive. So I will write plus RB multiplied by 10. And the sum of all moment about point A must be equal to 0. So from here we will get minus 30,000 minus this will be 16900 plus 10 RB is equal to 0. So what we will get is that 10 RB will be equal to 46,900, and this RB will be equal to, if you divide 10 on both sides, so you will get 4690 pounds. So this is the value of RB, reaction force by bricks at point B on the beam or base plate. Now you can find RA by using equation of equilibrium, that sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So RA is upward, so plus RA plus RB minus this 2,600 and minus 6,000, their sum must be equal to 0. So I can write RA plus RB minus 6,000 and minus 2,600 is equal to 0. So RA plus RB is 4690 minus 6,000 minus 2,600 is equal to 0. So when you calculate it, you will get RA will be equal to 3910 pounds. Now you have both RA and RB. So what we are going to do is that we will design this base plate. So what will be the parameters? So I will write the design must be based on the strength, and we will take the smaller strength, which is the strength of the pipe. So you have been given the allowable bearing stress of pine as well as for break. So we will choose this value. Clear? This will be, and at point A, at A, first we will calculate for A. So at A, we know that bearing stress is equal to bearing load over per unit area. So at point A, you can see this load is offered on this bearing plate. Clear? So we will write it as RA divided by area of base plate at A. And the bearing, we have taken the strength of pine. So strength of pine is 2.81 KSI. So 2.81 into 10 to the power 3 is equal to RA, which is 3910. And area of base plate, if base plate is like this, the width is given. This width is 3 inch, clear, and this length is not given. This length, which is length A. So I can write the area will be equal to LA multiplied by 3. Clear? So from here you will get LA will be equal to 3910 divided by 2810 multiplied by 3. And when you calculate it, it will be equal to 0.464 inch. And if you can see that if length is 1, we have been given that L should be 1 over nearest to 1 over 4 inch, which is equal to 0.5 inch. And if L is equal to half inch, it is 0.5. This is 0.25. Okay. As our value 0.4 is near to this 0.5, so L we select, we use length of this base plate will be 1 over 2 inch. You can also write it 2 by 4 inch, which is again 1 over 2 inch. So length of this base plate is 1 over 2 inch. Now what we will do is that at point B, our base plate B, we know that stress is equal to RB divided by area. So from here the strength is 2.81 into 10 to the power 3 KSI. RB is calculated as 4690 divided by area of base plate. For B will be LB into 3 inch. So again this length LB will be equal to 4960 divided by 2810 multiplied by 3. And when you calculate it, it will be equal to 0.556 since inch. So LB is equal to 0.556 inch. And we will take it nearest to 1 over 4 inch. So this is 1 over 4, this is 1 by 2, and 3 by 4 is 0.75. So our value is in between these two. So and for the closer, our safer design will be 3 over 4 inch. So we will choose LB is equal to 3 over 4 inch. 3 over 4 inch. Which is the answer of our this question. So this length of this base plate should be half inch, clear, and this length of this base plate should be 3 or 4 inch. And that was all about this problem 1-85. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it, and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching and supporting me. Welcome back. In this video, we are going to solve problem 1-91 that is taken from chapter number 1, stress, and book name is Mechanics of Materials by RC Hibbeler. So statement is, if the allowable bearing stress for the material under the support at A and B is 1.5 megapascal, determine the size of square bearing plate at A dash and B dash required to support the load. Dimension the plate to the nearest millimeter. The reaction at supports are vertical. Take P is equal to 100 kilonewton. So you can see this is the beam having support at A and B, and there is a uniformly distributed load of 40 kilonewton per meter over a length of 1.5 meter. And at this end we have P load, concentrated load, and this load is given as 100 kilonewton. So what you have to find is you have to find the size of this square bearing plate. Clear? So let's start with the solution. So what will be the first step is that if you remove this support at point A, so you will be having a vertical reaction force. Let this is represented as NA. And if you remove this this support at B, so you will be having a reaction force, vertical reaction force NB. So we'll find this NA and NB by using equation of equilibrium. So first equation of equilibrium that we will apply is sum of all moment about point A is equal to 0 and taking the counterclockwise moment as positive. Now you can see there is a uniformly distributed load of 40 kilonewton that will is acting on 1.5 meter length. So we will convert this load into a point load. So this load will be equal to 40 multiplied by the length over which it will be 1.5, and the unit will be kilonewton. Now sum of all moment about point A is equal to 0. So you can see the first load which is producing moment about point A is NB, and perpendicular distance is 3 meter, and this is producing counterclockwise movement, so it will be positive. So I will write it NB multiplied by 3 meter. Clear? The second moment that is producing due to this concentrated load, which is this one, clear, and the perpendicular distance will be this one, and this distance will be half of 1.5, which is 0.75 meter, and this is producing counterclockwise movement, so it will be also positive. So let me write this distance as well. This distance is 0.75 meter. Okay, so plus 40 multiplied by 1.5 multiplied by 0.75. The last moment that is produced due to this P load, which is 100 kilonewton, and the perpendicular distance is 4.5 meter, and this is producing clockwise movement, so it will be negative. So I will write minus 100 multiplied by 4.5 is equal to 0. Clear? So 3NB plus 40 into 1.5 multiplied by 0.75 minus 4.5 multiplied by 100 will be equal to 0. So when you solve this, again it's very easy. When you solve this, you will get normal force or reaction force at point B will be equal to 135 kilonewton. Now we will find this vertical force at point A. So how you will find this? So you will apply sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So you can see one force which is downward is this one, the other one is NA, the other one is plus NB, and this minus 100 will be equal to 0. So I will write 40 into 1.5 plus NA, which is upward, this is minus, here, plus NB is 135, and minus this P100 is equal to 0. So you will get it minus 60 plus NA plus 135 minus 100 will be equal to 0. So NA will be equal to NA plus 135 minus 165, minus 160 will be equal to 0. So NA will be equal to 25 kilonewton. Now you have both NA and NB. So you can see here that this is the vertical reaction by this support on this beam. Clear? As a result of Newton's third law, the load will act on this bearing plate will be again NB, but it will be compressive one. And similarly here, the load NA will acting on this bearing plate. Clear? So what we will do is that for plate A, let's say for plate A dash, let's say for example, this is the square plate. Clear? And this is square. So let one side will be equal to A dash. So this side will be also equal to A dash because this is a square plate. Clear? So we have a bearing stress is equal to bearing load at point A, which will be equal to NA divided by bearing area of A dash bearing area. Clear? So allowable bearing stress is 1.5 megapascal. So 1.5 into 10 to the power 6 Pascal, and NA is 25 kilonewton. So 25 into 10 to the power 3. And area of this bearing plate will be equal to A dash into A dash. Clear? So from here you will get A dash square will be equal to 25 into 10 to the power 3 divided by 1.5 into 10 to the power 6. So again, if you take square root on both sides, so you will get A dash will be equal to 0.1291 meter, and in millimeter it will be equal to 129.1 millimeter. So we will round it off. So we will select length of this bearing plate at A will be equal to 130 millimeter. Because it is given that choose nearest to the millimeter. Now we will move for plate at B dash. So let this is the plate at B dash, square plate. So let this one side which is equal to AB dash. So this will be also equal to AB dash. So allowable bearing stress is given as for the plate B, it will be equal to NB divided by area of this bearing at B dash. Clear? This will be A dash. Okay. Now you have the value. Allowable bearing stress is 1.5 megapascal. So 1.5 into 10 to the power 6 is equal to NB, which is 135 kilonewton. So 135 into 10 to the power 3 divided by area of this bearing plate at B dash, and that will be equal to AB dash multiplied by AB dash. So from here you will get AB dash square is equal to 135 into 10 to the power 3 divided by 1.5 into 10 to the power 6. Clear? And if you take square root on both sides, so you will get AB dash will be equal to under the root 135 multiplied by 10 to the power 3 divided by 1.5 into 10 to the power 6. And when you calculate it, you will get AB dash will be equal to 0.300 meter, or AB dash is equal to 300 millimeter. So what we will conclude that this plate at AB will be A will be equal to 130 millimeter by 130 millimeter. Clear? And plate at this B will be equal to 300 millimeter by 300 millimeter. That can be used to support the load shown in the figure. And that was all about this problem 1-91. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon. If you have any question, you can ask me in comment section. Thank you for watching and thank you for supporting me. Welcome back. In this video, we are going to solve problem 1-88 that is taken from chapter number 1, stress, and book name is Mechanics of Material by RC Hibbeler. So statement is the compound wooden beam is connected together by bolt at B, assuming that connection A, B, C, and D exert only vertical forces on the beam. Determine the required diameter of bolt at B and the required outer diameter of its washer. If allowable tensile stress for the bolt is 150 megapascal and allowable bearing stress for the wood is 28 megapascal. Assume the hole in the washer has the same diameter as the bolt. So you can see these are compound beams that are connected together by a bolt at B, and this reaction at A, B, C, and D only exert vertical force. All other loadings are shown over here. Clear? So you have to determine the diameter of this bolt. Clear? Diameter of this bolt and the washer that is used, outer diameter of the washer that is used in this bolt. So let's start with the solution. So as this is a compound beam, so what we will do is that we will first draw the free body diagram FBD of member or beam CD. So you can see this is beam CD. So there is a vertical reaction force of D at D, which will be FD. There is this load, this load. Now the bolt will exert a load that will acting downward on this, and this reaction force by the C will be upward. So we will draw its free body diagram. So let me draw it first. Let this is the beam. Here you have to draw it. This is point C. So we have FC that will acting upward. This is C point. This is your D point. Clear? So your force D will be also upward. FD. There is a 1.5 2 kilonewton load acting at a distance of 1.5 meter from this. So this distance is 1.5 meter. There is another load which is also 1.5 kilonewton and acting at a distance of 1.5 meter from the 2 kilonewton load. Now this is point B. Clear? So the load that is acted upon by this, the bolt acts on this member or beam CD is FB. The distance between FC and FB is also 1.5 meter, and from B till this node is also 1.5 meter. Now we'll apply equation of equilibrium in order to find this FB and FC. So what actually we are interested to find out this load FB. So what we are going to do is that we will apply equation of equilibrium that sum of all moment about point D is equal to 0 and taking the counterclockwise moment as positive. So first moment about point D will be equal to this force FB, and perpendicular distance is this sum of all this is 4.5 meter, and this is producing counterclockwise moment, so it will be positive. So I will write FB into 4.5. The second moment that is produced due to this 1.5 kilonewton load, and the perpendicular distance is 3 clear meter, and this is also producing counterclockwise moment, so it will be positive. So I will write plus 1.5 into 3. The third load which is producing moment is this 2 kilonewton, and perpendicular distance is 1.5 about point D, and it is producing counterclockwise moment, so it will be positive. So plus 2 into 1.5. And the last force which is producing moment about point D is FC, and this whole perpendicular distance is 6. This distance is 6 meter, and this is producing clockwise moment, so it will be negative. It will be negative. So I will write minus FC multiplied by 6 is equal to 0. So from here this will be equal to 4.5 times FB minus 6 times FC, and these two terms, this and this term, will give you minus plus 7.5. When move toward right side, it will be minus 7.5. That this is your equation number 1. Now what we will do is we will take the free body diagram of this beam AB. So you can see there is a vertical reaction force. The C will now act downward on this, and FB will be also upward on this, and there is a load. So we will draw this free body diagram. So I will write free FBD of member AB. So let me draw the free body diagram again. So you can see this is point A. So you will be having a reaction, vertical reaction force, which is FA. There is a 2 kilonewton load, 3 kilonewton load. You can see this is 3 kilonewton load that is acting at a distance of 2 meter from this side. Let this is point C. Clear? So at C you will be having a force that will be acting downward. Why? Because you can see that this force at C will be upward. So as there is Newton's third law, it will be acting downward. So this is FC. Clear? And same FB here is downward. Clear? So here it will be upward. So let this point is your point B. So here it will be upward, FB. Clear? And all the distance between these two forces are 2 meter. Clear? And from C to B it is 1.5 meter. Now we will apply equation of equilibrium. So the equation of equilibrium which we will apply is sum of all moment about point A is equal to 0 and taking the counterclockwise moment as positive. So about point A, one moment that is produced due to this FB, and perpendicular distance is 2 plus 2 plus 1.5 is 5.5, and this is producing counterclockwise moment, so it will be positive. So I will write FB into 5.5. Clear? The second moment that is produced due to this FC and perpendicular distance is 4. This is 2 and this is 2. So it will be 4 meter, and it is producing clockwise moment, so it will be negative. So I will write minus FC multiplied by 4. The third moment will be produced due to 3 kilonewton load, and perpendicular distance is 2, and this is producing clockwise, so it will be also negative. So I will write minus 3 into 2, and the sum of all moment about point A must be equal to 0. So what we will get is 5.5 times FB minus 4 FC is equal to 6. So from here you will get 4 FC is equal to 5.5 times FB minus 6. And if you divide 4 on both sides, so you will get 5.5 divided by 4 FB minus 6 divided by 4. And that will give you 5.5 divided by 4 will give you 1.375 times FB, and 6 divided by 4 is 1.5. And this is your equation number 2. Now what we will do is that put equation 2 in equation number 1, which is this one. You can see, so 4.5 times FB minus 6 times FC is 1.375, FB minus 1.5 is equal to minus 7.5. So 4.5 FB minus 6 multiplied by 1.375 is 8.25 times FB plus 6 multiplied by 1.5 is 9 is equal to minus 7.5. Clear? So minus 4.5 minus 8.25 FB is minus 3.75 FB is equal to minus 7.5 minus 9, which is equal to minus 16.5. And if you divide minus 3.75 on both sides, so you will get FB is equal to 4.4 kilonewton. So this is the force in the bolt. Now what we will do is that put FB in equation number 2. So you will get FC will be equal to 1.375 times FB is 4.4 minus 1.5, and you will get FC will be equal to 4.55 kilonewton. Okay, since we are in need of force in this bolt, so now we will calculate the diameter of this bolt. So what actually I will write is, we have been given allowable stress for this bolt is given as, which is equal to FB divided by area of bolt. So FB is 4.4 kilonewtons, so 4.4 into 10 to the power 3. Area of bolt is pi by 4, diameter of bolt square. Clear? So allowable stress for the bolt is 28 megapascal. So I can write it 28 into 10 to the power 6 is equal to 4.4 multiplied by 10 to the power 3 divided by pi by 4 dB square. So from here you will get dB square is equal to 4.4 multiplied by 10 to the power 3 divided by pi by 4 into 28 10 to the power 6. And if you take square root on both sides, so you will get the diameter of bolt will be equal to it will be 0.00611 meter. Our diameter of bolt will be equal to 6.11 millimeter. So this is the answer of our first part. Now we'll move towards second part, and in second part we have been asked to find the outer diameter of washer. So for washer, so you can see if this is a circular washer, clear, the inside diameter will be diameter of bolt. So this will be dB, and we will need diameter of washer, outer diameter. Clear? This is dW. So bearing stress, you can see that this washer is in contact with this wooden piece, so bearing pressure will be there. So this allowable bearing stress for this wooden will be equal to FB divided by area of washer. Clear? So FB is 4.4 kilonewtons, so 4.4 into 10 to the power 3, and area of washer is pi by 4 dW square minus dB square. So diameter of bolt in meter is 0.00611, so 0.00611 square. And allowable stress for the wood is 28 megapascal. Okay, so 28 megapascal. So 28 into 10 to the power 6 is equal to 4.4 into 10 to the power 3 divided by pi by 4 into dW square minus 0.00611 square. So when you calculate it, dW, you can now find it, dW square will be, or dW, when you calculate it, it will be equal to 0.0154 meter, or that will be 15.4 millimeter. Also make a correction that here allowable tensile stress for the bolt is 150 megapascal. So I will write it as 150 megapascal. Correct it, 150 megapascal. So 150 here, this will be also 150, and you will get this diameter of bolt. So make this correction, and that was all about this problem 1-88. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it, and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. In this video, we are going to solve problem 1-93 that is taken from chapter number 1 stress, and book name is Mechanics of Material by RC Hibbeler. So statement is the rod A, B and CD are made up of steel. Determine their smallest diameter so that they can support the dead load shown. The beam is assumed to be pin connected at A and C. Use LRFD method where the resistance factor for steel in tension is 0.9 and the dead load factor is 1.4. The failure stress is 345 megapascal. So you can see this is beam AC that is supported by two rod AB and CD that are made of steel. The dead load is shown over here. So you have, these are the pins supported at point A and C. So using load and resistance factor design method, so you have to calculate the diameter of rod AB and this diameter of rod CD. So let's start with the solution. So you can see that due to this dead load, clear, there will be a tensile stress in rod AB and CD. As a result, this rod exert a vertical force FAB on this beam and FCD on this beam. Clear? So we'll find this FA and FCD by using equation of equilibrium. So it is better to draw a separate view bar diagram for saving time. I am already drawing over here. So this is FAB, which is the force that is exerted by this rod on this beam, and this is FAC. So we'll find this FA and FAB and FAC by using equation of equilibrium. So first equation of equilibrium is that sum of all moment about point A is equal to 0, taking the counterclockwise moment as positive. So about point A, the first force which is producing moment is FAC, and perpendicular distance is 3 plus 3 plus 2 plus 2, which is 10, and this is producing counterclockwise moment, so it will be positive. So I will write FAC multiplied by 10. The second moment which is produced by this 5 kilonewton load and perpendicular distance is this 7 meter, and this is producing clockwise, so it will be negative. So I will write minus 5 into 7. The third load which is producing moment is 6 into perpendicular distance is 4 meter, and this is producing clockwise, so it will be negative. So I will write minus 6 into 4. And the last force which is producing moment about point A is 4 into perpendicular distance is 2, and this is producing clockwise, so it will be negative. So minus 4 into 2 is equal to 0. So we will get 10 FAC is equal to 67.67 kilonewton. And from here, this FAC will be equal to 6.70 kilonewton. Now this is FAC, so we can find FAB by using another equation of equilibrium, is that sum of all moment about point C is equal to 0, and taking the counterclockwise moment. So you can see that about point C, first moment is FAB and perpendicular distance is 10. This is producing clockwise moment, so it will be negative. So I will write minus FAB into 10, clear. The second moment will be 4 into perpendicular distance is this 8, and this is producing counterclockwise moment, so it will be positive. So I will write 4 into 8. This force is producing 6 multiplied by 6, and that is counterclockwise, so it will be positive. So I will write plus 6 multiplied by 6, and the last force is 5 into perpendicular distance is 3, and this is also counterclockwise. And the sum of all moment about point C is equal to 0. Okay, so from here, when you calculate it, you will get FAB is equal to 8.30 kilonewton. You can also find this by using this equation, that sum of all forces along y direction must be equal to 0, and upward force is taken as positive. So FAB minus 4 kilonewton minus 6 minus 5 plus 6.70 is equal to 0. So FAB is equal to minus 15 plus 6.70 is equal to 0. So FAB will be equal to 8.30 kilonewton. So you can use any of this in order to find this, but this one is the simplest one. Now we have FAB and FAC. We have been given as factored load, so we will find factor load, because you can see that we have been given dead load factor is 1.4. So this load FAB will be increased by 1.4 times. So 1.4 multiplied by FAB is 8.30. So this load will be increased. So it will be equal to 11.62 kilonewton. And similarly, FAC will be also increased by 1.4 because the dead load factor is given. So we have to multiply it. So this will be equal to 9.38 kilonewton. Now using LRFD, load and resistance factor design method, clear? By using this, we know that this factor which is given as pi 0.9, so this 0.9 into 0.9 into failure will be equal to for rod or for rod AB, 0.9 into failure will be equal to FAB, because this is in tensile, this is given resistance factor for steel in tension is 0.9, so this will be equal to area of AB, clear? Now what we will do is that from here 0.9 failure stress is given as 345 megapascal, so multiply by 345 into 10 to the power 6, clear, is equal to FAB is 11.62, and 10 to the power 3 will convert it into Newton, divide by area, so pi by 4 DAB square, clear? So what we are going to calculate is we are going to calculate DAB, so DAB square is equal to 11.62 into 10 to the power 3 divided by 0.9 into 345 multiplied by 10 to the power 6 multiplied by pi by 4. And if you take square root on both sides, so you will get DAB will be equal to 0.00690 meter, or DAB will be equal to 6.90 millimeter. So this is the diameter of rod AB. Now for rod AC, we will get 0.9 multiplied by failure is equal to FAC divided by area AC. So definitely you will get this will be equal to FAC divided by area AC, which is pi by 4 DAC square. So from here you will get DAC square will be equal to FAC divided by 0.9 multiplied by failure stress into pi by 4. And taking the square root on both sides will give you FAC is 9.38, so 9.38 into kilo, so 10 to the power 3 divided by 0.9 Failure stress is 345 megapascal. So 345 into 10 to the power 6 pascal and pi by 4. So from here, this DAC will be equal to 0.00620 meter, or this DAC will be equal to 6.20 millimeter, which is the diameter of rod AC. So this is diameter of rod AB and this is diameter of rod AC. And that was all about this problem 1-93. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching and supporting me. Welcome back. In this video, we are going to solve problem 3-13 that is taken from chapter number 3, Mechanical Properties of Material. And the book name is Mechanics of Material by RC Hibbeler. So statement is a bar having length of 5 inch and cross-sectional area of 0.7 square inch is subjected to an axial force of 8,000 pound. If bar stretches 0.02 inch, determine the modulus of elasticity of the material. The material has linear elastic behavior. So you can see this is the bar having 5 inch length, clear, and there is an axial load of 8,000 pound. And due to this load, it stretches, means change in length will be 0.002. So you have to determine the modulus of elasticity. First, we will write the given data. Bar length is 5 inch, cross-sectional area is 0.7, axial force is 8,000 pound, and the change in length or bar stretch is 0.002 inch. The material behave elastically, clear, and we have to determine the modulus of elasticity. So let's start with the solution. So as we know that modulus of elasticity, which is equal to E, elasticity, which is equal to E, and that E is equal to stress divided by strain. So we do not know stress and strain. So first we will define or we will determine stress. So stress here is equal to axial load divided by the area over which it acts. So axial load is 8,000 pounds. So I will write 8,000 pounds and area is 0.7 inch, square inch. So when you divide it, so you will get 11.43 into 10 to the power 3 pounds per square inch, or in term of KSI it will be 11.43 KSI. KSI is kilo pound per square inch. So you will get 11.43 KSI. Now what we will do is that in second step we are going to find strain, and you know that strain is equal to change in length divided by original length. Let me write original length, L. So change in length or stretch is given as 0.002 inch, 0.002 inch, and original length of this bar is 5 inch. So inch divided by inch, and you will get 0.000400, and it will be inch by inch or unitless because they will cut each other. Now modulus of elasticity, E will be equal to stress over strain. So you have both the value. Stress is 11.43 KSI and strain is 0.000400 inch per inch. So you will get the value of modulus of elasticity will be 28.6 into 10 to the power 3 KSI, which is the answer of our this question. So this is the modulus of elasticity for the given load and the cross-sectional area for the material. And that was all about this problem 3-13. I hope you have enjoyed this video. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. Also share my videos with your friends and help me in growing my channel further. If you have any question, you can ask me in comment section. Thank you for watching and supporting me. Welcome back. In this video, we are going to solve problem 3-18 that is taken from chapter number 3, Mechanical Properties of Materials. And book name is Mechanics of Material by RC Hibbeler. So statement is a tension test was performed on a magnesium alloy specimen having 0.5 inch diameter and gauge length of 2 inch. The resulting stress strain diagram is shown in figure. If the specimen is stressed to 30 KSI and unloaded, determine the permanent elongation in the specimen. So you can see this is stress strain diagram for magnesium alloy, clear, and we have to find the permanent elongation, clear, if it is stressed to 30 KSI and then unloaded. So let's start with the solution. So first step is that we will find the modulus of elasticity, E approximate, using this stress strain diagram. So how you will find this? So you can see this is the stress strain diagram and this is elastic limit. So in this elastic limit, if you look at this point, so this is the stress, let this is 13 and here it is 0. So 13 minus 0 divided by strain. At this point strain is 0.002, 0.002 minus original strain is again 0. So when you solve this, you will get modulus of elasticity is equal to 6.50 into 10 to the power 3 KSI. Okay, now we have find this. You can see that it is given that for 30 kilonewton, 30 ksi load. So it is loaded to 30 ksi. So again, at this load, the strain will be 0.0078. And after it is unloaded, it comes back, but it will not be, it will not come to its original position, and it will have certain strain. So how you will find that strain? That is what we call permanent elongation. So let me write it: permanent elongation. So from stress strain diagram, the strain recovered is along the straight line BC, which is parallel to straight line OA. We can find this permanent strain. How you will find this? Let this is point O, this is A, and this is B. Clear? So permanent deformation will be equal to, you can see at point B we have 0.0, which is total strain, so which is 0.0078. So again, when you release this load of 30 ksi, clear, it will not come back to original position, but it will have certain strain. So how we'll find that certain strain? That can be obtained by using the load 30 ksi. So 30 into 10 to the power 3 over the modulus of elasticity, which is 6.50 into 10 to the power 3. Clear? And that will give you the permanent strain in that object, and that is 0.00318 inch per inch. So what does it mean? It means that, let this is 0.00318. So after removing this 30 ksi load, it will come back to this, and you can see this line. This is point C. So this line BC is parallel to the initial line of stress strain diagram, and there will be a permanent strain will remain in this material. So I will also write it over here that this will be the permanent strain, epsilon P. This will be epsilon P. Now you can see that we know that strain is equal to change in length divided by original length. So for permanent strain, this permanent strain will be equal to permanent length divided by original length. So we are interested to find out the permanent elongation. So permanent elongation is equal to permanent strain into original length. So permanent strain is 0.00318, and original length or gauge length is 2 inch. So we will multiply these two, and you will get the permanent elongation, and that permanent elongation will be 0.00637 inch, which is the answer of this question. So this will be the permanent elongation in the originally gauge length of 2 inch magnesium alloy specimen. And that was all about this problem 3-18. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it, and don't forget to press the bell icon so that you can get notification about my latest videos. Also share my videos with your friends and help me in growing my channel further. And if you have any question, you can ask me in comment section. Thank you for watching.